unique approach for more than 20 years, and published in a very long track record of publications in very esteemed journals such as Nature Neuroscience. And he has a lot to say about the use of VR from a unique perspective of ecological psychology, motor learning, and other important aspects which will inform us today. He's going to be talking to us today about using ambulatory VR, which is a kind of a unique idea, and how we can use that to study and assess functional mobility. So thank you. Bill, we're looking forward.
Get established here. Okay, are we launched? All right, launched. Okay, well, I'm very, very pleased to be here and to be invited to speak to this group. We've just stuck our toes in the water a little bit of using VR for assessment and not quite yet rehabilitation, but we have some thoughts about that. But I want to start with just a little video. This is functional mobility, right? This is when you're out in the world interacting with these complicated situations, other people, animals, uneven ground, obstacles, moving obstacles. This is the sort of behavioral complexity that we are confronted with in the real world, and this is what we want our patients to be able to go back into when we're looking at rehabilitation of functional mobility. So that's the sort of phenomenon I want to try to address. And as a, all right, this is not responding, so I'll just use this. I'm a cognitive scientist. I study perception and action. I'm going to focus today on our research on the visual control of locomotion, but I will touch on some of these other questions of assessment and rehabilitation and try to draw some conclusions out of that. So I want to begin just by looking at our research questions and then move on from there. So the framework that I wanted to address is, just to give you a little bit of background about where I'm coming from. We think that we're studying this, all right? We've got a brain, sometimes it's a muscle, sometimes it's a nervous system, and that's what we're trying to work on. That's what we're trying to train or evaluate. But really, we're working with this, okay? We're working with a brain that's embodied in a physical body that obeys the laws of physics, and that body is embedded in a complex dynamic environment that is constantly bombarding us with information and physical constraints and so on. And it's this whole schmear that we are studying and trying to understand and trying to train. And so it behooves us, I think, to look at that whole picture. And that's the framework, the background that I come from. This is indeed what VR can do for us, right? So if we are, this real world is what we can, in some capacity, simulate with our virtual reality installations. And so we have the opportunity to work with that whole situation. So the background of what I do is I kind of have developed a framework that I call behavioral dynamics, which borrows some elements from dynamical systems theory, some elements from Gibson's theory of kind of the ecological approach to perception and action. And so I want to just briefly describe that and then kind of move into the research, some of the research that's motivated. I think I'm going to try to point at this screen, because there seem to be more people on this side of the room. So what am I talking about with behavioral dynamics? Well, we are that agent, that brain, okay, is in a body that's coupled to an environment. And we're coupled to the environment mechanically through the actions that we perform. And we're coupled to it informationally, right, through the stimulation, all the varieties of stimulation that we receive from that environment. And this is an interaction. And we can think of the agent as a dynamical system and the environment as a dynamical system that obeys the laws of physics. And these two systems get coupled together to create what we call a perception-action cycle. So What does that mean? Well, if the agent performs some action, applies forces within the environment that changes the state of the environment, that generates new information. The agent then takes that information and uses it to modulate the dynamics of their behavior somehow, which then changes the forces that are applied to the environment. And so it's this interaction creates what I call the behavioral dynamics. That is, at the level of the observed behavior, we have stable behavior, we have unstable behavior, we have behavioral transitions, and so on. And what the agent has at their disposal, right, are what I call control laws, these relationships between the information and the parameters and states of the action system. And so it's the coupling of that information to the parameters of the action system that gives us control of the situation. So we're, rather than imposing our will, right, on the environment, we're just tweaking the dynamics of the environment a little bit in order to get out the behavior that we're looking for. So that's what, when we're working with a patient, that's what the patient is struggling to do, right? Struggling to relearn, right, those relationships between the information, the sensory information available, and the remaining parameters or variables of the motor system. So the take-home message here is that, you know, the basic idea is that information modulates the dynamics of the system, so we have to understand the dynamics and the information. And when we're talking about mobility problems, right, they can arise anywhere in the system. They might arise from visual disabilities. They might arise from motor problems. They might arise from a mechanical skeletal problem. But it affects the dynamics of this entire loop. So the whole loop adjusts, right, to deal with that new constraint. So the goal, I would say, right, of rehabilitation is to try to restore the stable adaptive dynamics that we see in ordinary behavior. Now that may be involving new control laws, new relationships between the information and the variables. So when we're thinking about functional mobility, this is an attempt to try to look at this behavioral complexity that I was describing before. So we've got this gait hierarchy, as I think of it, where there's posture, then there's the step cycle, and then there's that trajectory that's generated by the step cycle in an environment. And at each one of these levels, there's a huge amount of adaptive variation, okay? The step cycle has to adapt to changes in the terrain, to, you know, the rough terrain problem, as I call it. You have to step over gaps, you have to step up stairs, avoid obstacles, walk on slopes. So there's, you know, a high-dimensional set of variation of the step cycle that has to be adapted to the environment. At the level of the locomotor trajectory, we steer to avoid obstacles, to reach our goals, to get through doorways, and interact with other pedestrians. So we're controlling the direction and speed of our walking, if we're talking about walking. So you get this unbelievable complexity, right, out of this set of little tasks, these multiple tasks. And for each one of them, right, there's a dynamic to that behavior, and there are control laws about how to use information to govern that behavior. And that's what we're treating, right, when we're dealing with patients. So, you know, the thing I'm trying to convey, I guess, is just the complexity of the behavior that we have to deal with. So the advantages of ambulatory VR, which is what I call walking around with an HMD on your head, is that we can capture that behavioral complexity and work with it. We can create more naturalistic tasks than we could in a traditional, say, physical therapy setting. It gives us the power to manipulate both the environment and the information that's available. And so we can really try to create the full range of adaptive variation for a patient or for a subject that they confront with the real world. So what I want to do is look at this for the case of locomotion at two levels, both at the level of the step cycle and how we adapt the step cycle, and at the level of the trajectory of locomotion that's generated. Okay, so that's the kind of background, the kind of framework. I realize I do not have a watch, which I guess is good for me, but bad for you. So let me start by looking at some of our research and other people's research on these questions. So this is the Venn lab where we do much of this research. It's a big open room, 12 by 12 meter tracking area, where we have a subject walking around wearing a head-mounted display. That's now a wireless head-mounted display. We finally achieved that last summer. So there's no tether between the person and the Wrangler here anymore. There's a head tracker built into the ceiling. There's 16 Qualisys cameras around the room so we can record gait kinematics. And this allows us basically to open up that perception-action loop that I described before to manipulate information as people are undergoing ordinary behavior. Okay? And so we can get in there and change things, manipulate those mappings in order to see how people behave. So one advantage of VR is it's very flexible. Okay, we all take advantage of that. But the other thing is that it allows us, I think especially for experimental purposes, to break the laws of physics and to break the laws of optics. So we can create situations that are impossible in the real world in order to test our theories about vision and action. So let's think about this problem now at the level of the step cycle. And I want to talk for a minute about the visual control of step length on rough terrain, so the rough terrain problem. I did a little work on this for running back in my postdoc with David Lee, but more recently there's been a kind of upsurge of interest in this again for walking. And we've already seen examples in the lightning poster sessions, right, of cases where people are working with patients on these sorts of problems. So in order to, if we're trying to train patients or retrain patients, I think it's a good idea to have a deep understanding of what it is we're trying to train, right? You have to have an understanding of what the step cycle involves and what the information that is used to inform the step cycle to know what to do in our rehabilitation setting. So this is kind of an appeal for basic research and referring to basic research in the context of rehabilitation. So for example, we've already seen people talking about this question of how do you avoid an obstacle that's on the ground, or how do you step onto a target, say a clear patch of ground that's on ahead of you on the ground. And one question I ask is, what's the information that allows us to do that? So there's, here's the target, here's the person approaching the target, and Duraghi et al. In Gilles Montaigne's lab in Marseille did some really interesting experiments where they varied the visual information available about that upcoming target on the ground. And in this condition, the target was just a dot in an otherwise blank field. So the only information available was the change in this angle, okay, which is the elevation angle of the target ahead of the person on the ground. So the elevation angle from the vertical. So that angle theta. The rate of change in that angle contains information about the time that remains before you are going to arrive at that target, the time to contact with the target. And it turns out that if you have that information about the time to contact, and you have information about the duration of your current step, that is enough to adjust your steps appropriately to hit the target. That provides enough information. So indeed, if you look at, this is their data with a single dot target, for the last step that lands on the target and the preceding 3 steps. And what they're plotting in each little plot here is the required change in step length against the observed change in step length for that step. And what you can see is 3 steps back, there's not much change. 2 steps back, just a little bit of change. It's really in these last 2 steps before hitting the target that you see large changes, large adjustments in the step length in the appropriate way. And in these last 2 steps, you've accounted for about 80% of the adjustment that's required to hit the target. So their results suggest that you're doing this based on time to contact, and you're doing that in just the last 2 steps before hitting a single target. So it's very online control, as we like to say. So some recent work by John Mathis and Brett Fajan have tried to manipulate the display to figure out when you need that information in order to control every step, right? So suppose you're walking on stepping stones or walking on uneven ground, have to avoid obstacles and hit targets as you're walking around. Well, this is an attempt to summarize several experiments. If you can see, so this is a situation in which you're walking across the lab and these targets or obstacles are being projected on the floor, and so they're adjusted in real time based on the gait kinematics they're recording from the subject. So in essence, if the subject can see 2 or more steps ahead, right, and then beyond that it's dark, they can still adjust their steps appropriately. There's low error. But if you can only see one step ahead, you start making lots of errors. Okay? Conversely, if, as you're approaching a target, if the targets disappear before they get to you, they disappear one step before they get to you, you have low error. Okay? So you don't need information in that last step. You need the information from 1 to 2 steps ahead of actually landing on the target. So another way to say that is, as here's step n minus 1, here's step n, there's that lands on the target. You need to see the target during step n minus 1. And their modeling suggests that during that step n minus 1, you're setting up the initial conditions for that last step to take full advantage of the passive dynamics of that step, right? So the gate system is a dynamical system. If you, it's like an inverted pendulum, if you just whack it, right, it'll take a step automatically, and there are now these passive dynamic robots that do this quite well with absolutely no control. And so what they're claiming is the nervous system, all the nervous system is doing is setting up the initial conditions for that passive dynamic system to let that system operate automatically in the final step. So you're tweaking the initial conditions and then letting the dynamics take care of the final step. Okay, so what I take away from all this is, again, information is used to modulate those gate dynamics, in this case time and contact information. You need that information one step before the final step that hits the target during step n minus. And essentially, you're walking one step at a time. In complicated terrain, you're adjusting every step, one step ahead, and you're not able to plan. Right? You're just running it up, doing one step at a time. So the online information is modulating your behavior continuously as you walk. That's what we're trying to train, right? When someone has got a gait disability. So I want to talk a little bit about the locomotor trajectory now at that next level up, which is where we've been doing most of our research recently. And this is essentially steering control. So the problem, as I see it, okay, as Lucas et al. 1977 showed, all right, is like this. You're moving through a complicated environment, you're chasing a target, you're avoiding obstacles, all in real time. And how do we do that? Right? So that's, we do this every day, maybe not quite at that speed, but when we're walking down the street in Philadelphia, this is exactly what we're doing. So how do we steer through a complex, changing environment like that? And we're going to propose that we do this in an online controlled fashion, much as we saw with the step cycle. And the trajectory that we take is an emergent behavior. It's not a pre-planned trajectory. And I think the same thing is probably true for our movements when we're avoiding obstacles to get to a target. We did a number of experiments looking at the information that tells you about the direction of locomotion. So information about optic flow. When you're moving through an environment, it creates an optic flow pattern. And we're able to determine our direction of travel with an accuracy of about 1 degree of visual angle from optic flow patterns alone. There's also proprioception from your feet and ankles as you're walking that tells you about your current direction of travel, your current heading. And so in some experiments in the Venn lab, we tried to pull these things apart by shifting the optic flow pattern with respect to the direction that we're walking. So we presented displays that look like this. This is the kind of subject's eye view of someone walking through the environment. You can see that optical expansion occurring as they're lumbering right toward this target, the doorway. And it turns out that both the optic flow and the proprioception from your feet and ankles contribute to your steering control. And here's a sample from one condition where here's the trajectory predicted if you're just relying on proprioception. Here's the trajectory to the goal predicted if you're just relying on optic flow. And people go somewhere in between, and exactly where they go depends on the amount of optic flow that's present in the display. So if the optic flow is present, you take full advantage of it. So that's the basis, right, for steering control. And what we've been doing over the last decade is asking this question, all right, how do we then generate a locomotor trajectory based on this information? Same sort of question exists for generating a reach trajectory. So we've been developing what we call an Austrian model, and this is work with Brett Fajan and others since that time, where we take that sort of complex steering behavior that we saw in our very first video and try to break it down, decompose it into 4 essential components, which I'll try to go through. So here's the kind of general locomotor behavior, and we say, all right, as you're walking down the street, you have to get to your goal. You have to avoid obstacles on the way. But the goal could be moving if you're trying to catch a friend. The obstacles could be moving if you're trying to avoid other pedestrians or cars. And so there are at least 4 elementary behaviors. And what we've been trying to do is study each one of them in the event lab, model each one as a simple dynamical system, and then combine these components together to see if we can generate more complex behavior based on just superposition of these basic components. So the essential idea is, here's this person walking in some direction that's specified by the optic flow in this case. Here's the direction of your target, if it's a goal. And so to walk toward the goal, what do you need to do? Well, you need to turn, right, to null this heading error between the direction of travel and the target. If, on the other hand, this is an obstacle, what do you need to do? We need to increase this angle so you don't hit the target. It's very simple, but those changes in those angles change over time, and so there is a dynamic, right, to that behavior. So we're going to try to look at that now, break it down for each one of those basic elements. So what about steering to a goal? Well, the basic idea here is you're just nulling that heading error that I identified. And we model that in terms of a little mass spring system. So it's as though the direction that you're traveling is attached to the direction of your goal by a damped spring. So as you walk forward, your heading is pulled into alignment with the direction of the goal. It's a very simple idea. It turns out that we can model this quite well. That gives us a kind of potential function where here's the goal direction at the 0 goal angle. But as you get closer to the goal, the well gets steeper, right? So it attracts you more rapidly in the direction of the goal. So you turn faster if you're close to the goal than when you're far away. When we simulate that using a little agent-based simulator, that's the behavior you get. Okay, so that people will turn and then walk directly to the target. We created this model basically by collecting a lot of data in the event lab where we presented targets at different positions and different distances, and then looked at the paths that people traced out. Here's the time series of that heading angle, so it goes to 0 over time. And the model generates trajectories that are very similar to the human trajectories, and there's a time series dynamics of the behavior are also very similar. So the mean, our squares are very high. So we're doing a really good job at describing how people steer toward the target. So essentially the goal behaves as an attractor of your heading as you're walking around in the world. But what about obstacles, right? You're encountering obstacles on the way to the goal. And so in this case, we just did a simple thing. We said, all right, we're going to make that spring a positive stiffness instead of a negative stiffness. So now the spring is pushing your heading direction away from the direction of the obstacle, but that force has to decline as you steer around the obstacle. And so you get a little potential hill that's pushing you away from the obstacle. Here's a simulation of that. So we're deviating around the obstacle on the way to the goal, avoiding a collision. And again, this is based on data we collected in the event lab, where here's a subject walking to a goal. Here are 3 different obstacle positions, and we deviate around them. Now the time series of that heading error increases over time. So the direction of the obstacle is acting like a repeller of your heading and driving you away from it. And the model behaves quite similarly to the human data. So again, simple physical model does a pretty good job of describing the behavior. The obstacle, in this case, behaves as a repeller of heading. So you can keep going, right? So now, what about if the goal is moving? So you're now trying to intercept a moving target. Well, if you sail, you've encountered this problem, right? Because if you're sailing with respect to another boat, and that boat remains in a constant compass bearing, then you're on a collision course with that boat. So this is an attempt to describe that here. So there's the other target. Here's you, and if you're moving so that that target remains in a constant direction in space, constant bearing direction, then you're on a collision course. So you can intercept the target that way. So all this does now, the equation is basically the same idea, but now we're nulling change in that angle, nulling change in the bearing direction of the target, rather than nulling the angle itself. And when you simulate that, here's the target, here's the person who's trying to intercept, and you get these kind of successful interception paths on the target. This is the sort of data that we base the model on. So here's a target moving in different directions and different speeds in the world. And in this case, the human data is in red, and the model is the dashed line that's basically right on top of it. These are the heading errors over time. And as you see, the heading error increases to some constant value. So that's the constant variant. You're heading, in this condition, about 20 degrees in front of that moving obstacle, and therefore you're on an interception path. So the interception path, in this case, is what is attracting you, right, by nulling change in the bearing direction. For a moving obstacle that you want to avoid, we're just going to do the opposite, right? So now we flip the stiffness sign again. So now we're increasing the bearing direction of the target. We don't want to keep it constant. We want to increase change in that bearing direction. And so we get behavior that looks like this. So we're now avoiding that moving obstacle on our way to the goal. Okay, so that's a set of 4 components, right, that just do a pretty good job of describing individual types of behavior. So we've modeled each one. The question is, if we start putting them together, can we explain more complicated behavior, more complicated situations? So can we do these act as basic elements, right, that then we can superpose or combine to describe complex behavior? And this, in many ways, is kind of what Norm Nadler was doing yesterday. And his approach was to kind of model the behavior of individuals, like this Grand Central Station scene here, was to model the behavior using a set of rules that he derived. We're trying to base those rules on empirical data, right, and trying to model those rules using dynamical systems rather than rule sets. But the goal is similar, right, to try to describe how people behave in the real world. And so if we take Grand Central Station, right, this complex environment, can we try to model something like that? Can we simulate those trajectories adequately? Here's an example. So here's a person dealing with a model dealing with 3 moving obstacles. And indeed, the model manages to avoid them and get through on a path to the target successfully. So we've done a number of these simulations that are able to succeed in dealing with complex environments. The question is, does the model do what people do, right? Can we actually describe human behavior this way? So last summer we said, all right, we got to collect some data, right, on people moving in these complex crowd scenarios. And so we created what we call the sales swarm, right? We took over Sales Hall at Brown University, set up our 16 Qualisys cameras so we could track people's head positions while they wore these funny antennae. And so we set up a bunch of scenarios and tried to collect as much crowd data as we could in a week when we had this set up. So in this case, the Grand Central Station scenario, we had 20 people crisscrossing the room back and forth. There were 10 obstacles in the way, so they had to avoid the obstacles and avoid each other. There were little numbers on the opposite wall that defined their goal, so they would walk across the room, look at a list, get the next goal number, and then walk back across the room to a different location, and just keep doing this for 3 minutes. All right, so we collected a ton of data in this way. The hard part, as you all know, is tracking the data. So we're still processing these data files from this week of data collection. But that's the sort of thing you get. Sometimes you lose tracking. People blip in and out of existence, which makes it a little hard to simulate. But those were the conditions under which we were operating in this data collection. So now the question is, can we simulate that, right? So can we do it at 2 levels? Can we simulate, how well can we simulate individual trajectories? Which is a really hard problem. I mean, it's like, this is a statistical mechanics problem. It's like, how do you simulate the trajectory of an individual particle in a gas? You're only going to be able to do so well, right, until noise begins to overwhelm you. So then there's this sort of next level of question, well, can you simulate the traffic patterns, right, that these collection of particles take? So here's a replay of one trial of data on the left, and you can see people kind of blinking it on when they come into the tracking area. And here's a simulation of that data, where we took each pedestrian, each subject, took their initial conditions on each trial, and then just ran the simulation. So we're simulating all these people, and we're simulating all of their interactions, and seeing how well we can do. We're still developing a divergence measure to see how closely the model diverges from the actual data, so I don't have a quantitative answer for you. But you can look at the traffic patterns, these blue dots that are laid down, and you can see that there are certain pathways that get more heavily traveled than others, and that seems to be captured in the simulation. Interestingly, we can do a reasonable job of this with this sort of minimal model, where we just have each agent has a goal, they avoid stationary and moving obstacles, and there's an emergency braking component in case they get stuck in a position where they have to decelerate. And that does a pretty good job of capturing this sort of behavior. We're looking at other scenarios too. So this is one, well, the more interesting one, is a counterflow scenario where two groups are passing through each other. So we set up a group on each side of the room, say, just walk to the other side of the room and pass through each other. And look what happens. They form these nice lanes, stable, spontaneous lane formation. Okay? And so the question is, can we reproduce that, right? And so here's an example of a simulation of one trial of data, where there are two groups passing through each other, and lo and behold, if we just add the obstacle avoidance component, so this is in a crowd simulation like this, each neighbor is matching, each pedestrian is matching the velocity of its near neighbors, so they're walking together as a group. And people who are walking in a different direction are treated as moving obstacles. And so the opposing groups are treating the groups with the opposite t-shirt color, right, as obstacles. And that's enough to generate these lanes, as you can see, the blue and the red lanes kind of segregate as they're walking through, and those lanes persist for a period of time. So again, a few simple components, right, are enough to generate these global patterns of behavior. So I'm going to claim, right, we're still testing this model, but I'm going to claim that we can account for human behavior, pedestrian behavior, in fairly complex environments, including interactions between pedestrians, and we're now working on the formation of crowds and how crowds actually cohere out of a bunch of individuals. You know, very similar to what Norm was trying to do yesterday. Okay, so that's a summary of research. Who's watching the time? How much time do I have left? 14. Okay, that's not bad. All right, so let's turn to assessment a little bit. So now that we've got some of how locomotion is controlled at the gate level and the trajectory level, how are we going to assess certain kinds of mobility problems? In this case, what we need to do is to test the perception action cycle, right? Rather than just study it. We need to assess how stable, how accurate, how functional is it. We want to try to create a set of tests that are sampling that range of functional mobility we saw in the very first video. And what's nice about VR, of course, is that then you can create these sort of naturalistic tasks and have a set of tasks that you can use to assess the broad spectrum of functional mobility. And this is an image from Joyce Fung's lab, which is, you've probably all seen this before, but here someone is walking on a treadmill in front of a screen. So it's a situation that's a little more amenable to a clinical setting with a screen and a treadmill. Well, so the goal here is to go beyond the kinds of current tools that are available to clinicians and physical therapists, and to try to add measures of functional mobility. This is what we're all trying to do, right? So the idea would be to try to develop a battery of naturalistic tasks that will allow us to sample natural behavior and somehow to test the range of adaptive variation we see in the real world to see how well people, to test how well people might be coping with that range of variation. I'm going to briefly mention at the level of the individual step cycle the kind of natural gait dynamics that we see in stride intervals in just walking over level ground. And this is work by Jeff and others that have followed. One measure of the patterns of variability in our stride to stride time intervals is to use statistical measures such as detrending fluctuation analysis which allow us to get some sense of the kind of noisiness, right? What's the structure of noise or the structure of variability in our ordinary gait patterns? And as Jeff and others have shown over the years, normal gait has this sort of alpha value. This is a measure from detraining fluctuation analysis that I will not try to explain, of about 0.75. It's like pink noise or fractal noise. It's kind of a self-similar structure at different time scales in ordinary gait. That may reflect the kind of adaptivity of normal gait, right? We're able to make adjustments on different time scales as our posture and balance conditions vary. On the other hand, in certain kinds of aging and disease, you see different alpha values. So if you think of this as a continuum of different amounts of dynamic structure, on the left end of the continuum is just white noise, random variability. And that seems to be, with a DFA alpha value of 0.5, that is what you see progressively in aging and in central nervous system diseases like Huntington's disease. On the other hand, if you have peripheral impairments like peripheral neuropathy or an ACL injury, you tend to see alpha levels at the other end of the scale. That is brown noise or correlated noise, right? Over-regular patterns with alpha levels of about 1. So this may be an assessment that's now getting used, right, to assess different types of gait impairments and disabilities. So that's one type of assessment at the level of the step cycle. We've been doing a very preliminary study of the locomotor trajectory level in an ACL injury situation. So if someone has an ACL injury, does that show up in the trajectories that they produce as they walk? So could you measure those trajectories as a marker of how well people are doing, right, in recovering from this injury? And this is a collaboration with several orthopedic surgeons, and Chris Ray, who's here, Hugo Bergman, and Susan DeAndre, who's a biomechanist. So the idea, in this study, we took 8 ACL injured patients, measured them pre and post-surgery, and 1 year after surgery, and we're still analyzing the post data, and 8 age and sex matched controls to see if we could develop some tasks, right, that might assess their locomotor trajectory as a reflection of their ACL injury. So Martin Jean-Lajoie was with us a few years ago and developed this figure 8 task. So in the virtual world, there are 2 obstacles, and the person is supposed to walk a figure 8 pattern around these obstacles, as you see here. And the advantage of this is, so we're basically studying people's ability to make a turn. And we can vary the curvature of that turn, and we can vary, and there are straight sections here as well. So you can see them going into the turn, and there's a right loop and a left loop, so the affected limb is on the inside of the turn in one case and the outside of the turn in the other. So it allows us to create some conditions that assess this variation. We also then compared self-selected path and speed, what they preferred to walk. We would control their speed with auditory feedback and look at how that affected their path. Or we would control their path by following these dots, these kind of breadcrumbs, and look at how that affected their speed. And we recorded gait kinematics and the head trajectory in this situation. So just a few preliminary results. These are the pre-surgery patients, so this is as a marker of the injury. There is this nice relationship between speed and radius. So the radius of the path increases as the speed increases for these patients. All right. So if you make them go faster, right, the radius of the turn gets bigger. So they're taking less sharp turns, basically. Interestingly, when the injured knee is on the inside versus outside of the path, the behavior is different. And in a nutshell, when the injured knee is on the inside of the turn, people freeze that knee so that to avoid rotation, right? You're normally pivoting on that inside leg when you make the turn. The patients don't want to do that, right? So they stiffen up the knee to reduce the rotation, and this shows up in their trajectory, so that when the knee is on the inside of the turn, this is the biomechanical analysis, the amount of rotation is less than when the knee is on the outside of the turn. So it looks like, there's some ways of analyzing these trajectories that will give us some insight into what's going on at the level of the knee, in this case for an ACL. But this raises a bigger question, which is, we're talking about this sort of behavioral complexity in the world, and how do we decompose that into a set of basic tasks, right? How do we figure out what those tasks are that we should be testing in the lab and then trying to train? Well, I just did this intuitively. I said, well, there's the rough terrain problem, there's stepping over gaps, there's climbing up steps or stairs, there's stepping over obstacles. But there may be a principled way to do this, and I just want to point you toward this new work by Victor Jersa and his colleagues toward structured flows on manifolds, right? Whatever the heck that means. Basically what they do is they're able to take high-dimensional data. So let's sample people just walking around in the world, like in that first video, all right? And then take that high-dimensional data and project it onto a low-dimensional manifold. So we do a principal components analysis, get out the dimensions of variation that we actually see in the data, represent that in a lower dimensional space, and then we can look at the topology of the dynamics in that space. So here are some examples of this low-dimensional manifold. There are certain patterns where you get limit cycle behavior, or monostable behavior where there's an attractor, or bistable behavior where there are two attractors. And so we may be able to take this complex behavioral sequence and segment it up into things that have a common underlying dynamic. And that would give us a principled way of trying to identify different types of tasks that we can assess and then possibly train. Okay, so let me briefly move on to rehabilitation, which I am not engaged in. But I think, having thought about this problem, there's some lessons that we can take, right? So the goal of rehabilitation, I would say, is to restore the dynamics of the perception action cycle. You want people to be able to behave stably, right, and to use the information available to adaptively regulate their behavior. So in rehabilitation, we have to worry about this adaptive variation that we see in the real world at all levels, and somehow prepare people to go back into the world where they're faced with that level of behavioral complexity. So how do we do that? So I'm going to think about this again in the context of locomotion. How do we retrain locomotion? Well, if you open any textbook on motor learning, right, there are some principles that I think are directly applicable. So motor learning says we learn more effectively with variable practice. Okay? Well, that's a direct reflection of the adaptive variability that we're faced with in the world all the time, right? The initial conditions for our movement are constantly changing. The orientation to gravity is constantly changing. The obstacles we face, the challenges we face in the environment are constantly changing. There's a natural range of variability, and variable practice is one way of sampling that natural range of variability. Also, random practice instead of blocked practice, right? So if you have a set of tasks, these locomotor tasks that you're trying to train, it's more effective if you randomly mix them up than if you do an intensive block of training on a single task. And this gets shown time and time again in motor learning studies. Learning, it seems to be specific, right? It's task specific. There's a specificity of learning. So if we're going to sample, we got to sample natural behavior and train people on the tasks they really are going to face in the real world if we're going to hope to transfer back to the real world. And finally, something that most people do is kind of present a graded difficulty of tasks, right? So there, you set goals for the level, you increase the difficulty of those goals, you provide feedback, and all of these things improve learning. They also affect the motivation of someone to get through the rehabilitation program, right? If you're trying to beat the level, right, that's highly motivating. So there was an inspiring study by Birelman et al. A couple of years ago that really showed that doing this sort of naturalistic training on behavioral tasks, on gait tasks, in this case it was avoiding obstacles, so stepping over obstacles, really did have some benefit, right? In a VR, from training in a VR context, it did translate back into some real world locomotion. I'm going to, I think, skip given the time. Am I doing that time? Maybe I'll talk about this briefly. So take that case of the dynamic structure of variability in gait over even ground, or flat ground. If you've got a patient who's got a DFA alpha right, that's too low or too high compared to normal gait, could you retrain, right, that structure of variability, that dynamic complexity of their gait? Could that be retrained? And so Chris Ray is going to talk about this tomorrow afternoon, and Adam Kiefer is also working on this project, where what we did was we said, all right, can we train variability? Well, let's give people a visual metronome as they're walking in a training session. And they have to synchronize their steps to the metronome. This is a common thing. But what if we made that metronome fractal, right, or noisy? What if we added different types of noise into that steady rhythm of the metronome? So this is a flashing light, okay, that people are trying to synchronize their steps to. And we had three conditions. So there's a baseline with no metronome to measure the normal variability of normal gait on a treadmill. Add white noise into the metronome. Okay, so the metronome now has an alpha level of about 0.5. Or add brown noise into the metronome, like correlated noise, and has an alpha that's close to 1. So can we push people, right, in one direction or the other? So people walked with each metronome for 15 minutes, and we measured their variability. And indeed, the stride variability on the metronome shifted in the direction of the metronome. Stride variability on the treadmill shifted in the direction of the metronome. So here's the baseline, DFA alpha, about 0.76. And it shifted lower when they're walking, trying to synchronize with the white noise metronome, and it shifted higher when they're trying to synchronize with the brown noise metronome. So it's malleable, right? People will indeed step, right, in synchrony with this fractal or structured noise. So this sort of thing has been found previously for tapping, okay, and also for walking in a similar kind of experiment. But the question is, for rehabilitation, will that get retained when you turn off the metronome, right? So it's fine, some people can synchronize with it, but you're going to affect the variability of their structure after the fact. And so this is, again, preliminary results where we just turned off the metronome immediately and measured the stride for the next 15 minutes. And indeed, so here's the brown noise metronome, pre-test without the metronome. During the metronome presentation, the alpha shifted up, and that was retained when you shut off the metronome, right, in the following 15 minutes. So the question is, how long will that be retained? And can you, with training, probably multiple sessions of training, really shift the gait dynamics of patients? And Chris, I think tomorrow is going to talk about some experiments where he did other types of stimuli besides a flashing light to see if there are more or less effective ways in training people to an external stimulus. Okay, so it looks like at the level of step cycle we can influence the dynamic complexity of gait, and hopefully this will have some applications. There's a paper by a group in the Netherlands, and Peter Beek, who I know is involved in this project, about trying to retrain people to deal with the rough terrain situation. This is people who've had hip fractures and are recovering from surgery. And what they're proposing to do, this is a clinical trial that's just beginning, so they published a protocol this year, is to train people on, they're now trying to sample different types of natural tasks. And they're going to try to train people on different types of tasks. So a stepping stones task where they can vary the spacing and frequency of the stepping stones, stepping over gaps where they can vary the size and frequency of the gap, controlling your speed to stay within this moving window, so you have to speed up and slow down. And so these things are samples of natural gait behavior. They're task-specific practice. And what they're doing is they do some training in each one of these, and then they introduce a game where they mix them up together in various combinations, some of them simultaneously. So they're doing that sort of random. And so you're trying to get at this range of variability in natural behavior, and the difficulty levels will increase. So we'll see, right, how this does. But it seems to follow those principles of motor learning that should produce some interesting results. So the goal of rehabilitation is to restore the dynamics of the perception action cycle, and I think it's critical to be training that adaptive variation for each of these natural tasks. So now I will conclude right on schedule. So what are we trying to, why do we want to use VR? What are we trying to do with VR? Well, we want to obviously provide some sort of rehabilitation training that will transfer to the real world in a maximal way. To do that, I think there are a couple of lessons, right? I think we need to sample the behavioral complexity of the real world, right? Because training is task specific, so we need to sample that behavioral complexity, train on multiple tasks, mix those tasks up, okay, so we have random training, and try to somehow create the full range of adaptive variation that we see in the real world through variable practice. So again, applying these basic principles of motor control, I think, jives very nicely with my understanding about the dynamics of perception and action and the use of visual information to modulate the dynamics of behavior. So I'll stop there. Happy to try to answer questions.
Okay, so I get to go first because I'm already at the conference. Okay, Bill.
You should step to the back.
I know. Thank you. Fantastic talk. Really intriguing ideas. What I'm missing, and I'm wondering, I would bet you've thought about it, is that most of your training is externally generated goals. Where does the internal planning come into this? You know, I know for myself, and I bet many of us think about this, that when I'm just walking down the street, don't care where I'm going, I'll walk a straight line. I don't mind following someone else. But if I'm in a hurry, I do a lot of weaving around people, and I will cut and cross. So where does that connection take place?
Yeah. I mean, so the way I think about that particular problem is you've got this sort of repertoire of tasks, right? These dynamics that you can enact depending on your situation. And so those can be, this is kind of the action selection problem, right? So those can be selected depending on what your current goal is. So given your current goal, you may increase your velocity. That's going to change the conditions for all of those simple components of behavior that I was trying to characterize. But I think we can model that, right? And I think that we've looked at actually at some variations of speed for these things. So I think it's very consistent with that idea. These are kind of, you can think about this as kind of intentional dynamics, right? So it's like you're selecting a dynamic based on your goals, right? And then once you've selected that dynamic, then the behavior will kind of follow it.
Bill, thank you for that wonderful talk. So I'm going to sort of get into some conceptual issue here. Sorry, but so in rehab, we, at least in stroke rehabilitation or stroke rehabilitation of people with neurological dysfunction, we tend to try to take this noisy system and try to find some stability in it. And we do this through various ways, but we don't. The issue that you've raised and which you've talked about is the variability of the system. So if we go back to the Wordsworthian notion of redundancy and variability, we can think of this as a system that actually has lost its variability. And so it's kind of like in conflict. There's these two conflicting things. One, we want a stable system, but on the other hand, we have a system that lacks variability. So and we know from dynamical science that without variability, we can't have a stable system. So where do we go? Do we go more towards increasing variability in the system that's already very variable but doesn't have any structure? In other words, I'm arguing for structured variability.
Yeah.
And I'd like to maybe make some comments on that.
I mean, in the context of rehabilitation, you can figure that out. I have no idea.
I need your help.
I have no idea. But clearly, I mean, I think for me, one of the morals of the dynamical system story is there's stability on the one hand and there's flexibility on the other hand. And so if you have a purely stable system, you're locked in, you can't change, you're just stuck in an attractor where you get perseveration, right? Where you get somebody becoming very rigid. On the flip side, so I think, right, the variability or the flexibility comes from the use of information to modulate the state of the system, or modulate the parameters of the system. So it's variability that's adaptive, it's functional, right? Variability or adaptive flexibility. And so what I think you're seeing in patients where there's noise that's been added to the nervous system, perhaps, and so they're trying to overcome the noise by becoming very And so they're fighting the noise, right, and going over toward the stability. But somehow they have to reintroduce this adaptive flexibility, right, despite the noise. And how are you going to get that to happen practically, you know?
No, I think that's the challenge for rehabilitation. Anyway, I'll let you.
We'll talk more.
Okay, thank you for your very interesting and complex talk.
Sorry.
My question refers to the research to the four-component model of steering control. And you very convincingly showed that it simulated normal behavior of people. But did you ever think of or experiment with leavening this model in systematic fashions in order to simulate patient behavior of different neurological or orthopedic conditions in order to understand better what's going on in these patients?
Yeah, so we're pursuing that in one instance, right, which I didn't talk about, but which Adam Kiefer has been involved in, which is people with visual disabilities. So we've been looking at tunnel vision patients or hemianopia patients who've lost vision in all the periphery of their visual field or one half of their visual field, and how they deal with obstacles, right? So if you ask these patients what their nightmare situations are, it's crowds, public spaces, public transportation, where there are things coming in out of their blind field, right, and they can't anticipate. So we've been doing some experiments where we're looking at these tunnel vision patients, presenting stationary and moving obstacles to them, and then trying to model their trajectories. And the idea is, at what point can we lesion the model, right, to reproduce the kinds of behavior that we see? And it turns out that basically we lesion the model at the level of input, okay? So there are two classes of patients. There are patients who developed a scanning strategy, so they detect the obstacles. And so we actually have them push a button when they detect the obstacle as they're walking. So the patients who detect the obstacles regularly, their trajectories look just like normal people, right? Normally sighted. But it's the group that fails to detect the obstacle, that doesn't have a scanning strategy to detect the obstacles. They're the ones that just blast ahead and walk straight through and often have collisions. So, you know, that suggests that what needs to be trained, right, in rehabilitation might be a strategy for identifying, for localizing these obstacles. But that's a simple case, and that's as far as we know.
The other one would be more interesting, lesion in the connection between perception and action, and whether this fits with patients with, for example, white matter lesions between frontal and parietal cortex.
Yeah, I should just point out this is a pretty functional model,
yeah,
right? So it's not really a neural model, and I'm not sure it will map on directly.
But the modeling is a very promising approach, I guess.
Thank you.
Hi, maybe it's a follow-up to a previous question, and again on the crowd dynamics and obstacle avoidance. You show that it's matching trajectories very well, but it's also matching velocity.
Good question. Yeah, so what we found up until the last component, moving obstacles, people tend to walk at a preferred velocity, and the velocity is pretty stable. They steer, right, and it's more energy efficient, right, to steer than it is to accelerate and decelerate. And so under most conditions, people will just change their heading while keeping a constant speed. Except when you're faced with avoiding a moving obstacle. And in that case, people will slow down if they're going to pass behind it, or speed up a little bit if they're going to pass in front of it. And so we're about to submit a paper where we have modeled that as well. And it's the same principle, interestingly enough. So essentially, you're trying to avoid keeping that object at a constant bearing. Okay? And you can do that by speeding up or slowing down, or you can do that by changing your direction. And so we now have two components to the model, one that modifies your heading direction and one that modifies your speed, both driven by the rate of change in that angle. And so they basically cooperate, but they're coupled through the world. It's not a more complex control system. There's like one control principle for speed and another control principle for direction, and they work together.
Maybe another situation is when you're trying to, when you have a moving target and
that's going too fast.
You see that's going too fast.
That's right. So we did an experiment where we created conditions where the target was going too fast. And people do speed up, right, in that situation. And so I'm not satisfied with our model in that.
So will we simulate a football match next? Or?
You know, that's a really interesting question, because I originally thought we would. But it turns out that sports situations are often highly strategic, right? So there's this level of cognitive strategy that gets imposed. And so sometimes you see like this constant bearing strategy. So we did actually analyze some data on football tackles. And sometimes you see it describes the situation quite well. When people are instructed, you know, to cut right or cut left, it just falls apart, right? So they're doing something else. There's some additional strategy that's imposed on top of this. And so you have to model that by a different control.